All right, welcome to Tuesday. I think we're supposed to get some snow today, at least up north they are, but I don't know if we'll get any here. Let's see. I kind of miss the snow just a little bit. Um, so. All right, quick reminder, tomorrow is Community Day, so don't go to class tomorrow. So, instead, you should be volunteering. I'm sure you're all signed up to volunteer someplace because volunteering helps you feel better, helps your whole mental health, giving back, helping others. It's a very self-centered thing to do because we do it just to make ourselves feel better. You think we do it to help others, but no, most of us just do it to make ourselves. Well, I'll be volunteering at the Makerspace, and I'll just spending 2 hours cleaning will just help my mental health so much. It'll be very good to do. So just encourage you to serve your own interests and do that by volunteering to help others tomorrow. There's lots of community day stuff, but and I assume you're already doing something there. But if you're not, we're still looking for 2 more people for help clean up at the Makerspace. We'll be there from 10 till noon tomorrow, and then we'll have some food there. If you need a ride there, we have people driving and stuff like that. So do the sign-up sheet and do that. So we're going to go, from image. We're kind of looking at some different ways of doing neural networks and different custom setups here. And then we're kind of looking at these individually because they're developed individually, are still used, but eventually these will be combined together to do more complicated stuff. So far we looked at image processing and convolutional neural networks, and those serve, as the underlying layers to anything that does any image recognition or any image generation uses these convolutional neural networks to, or parts of them to do image generation stuff. So we're going to leave images for a while, and images are very costly to process because there's so much data that, each image is a lot of data. So our training times has kind of gone up. I don't know if I know a number of people were running into problems on Sunday and stuff. So trying to get this stuff trained and I kind of warned you, but that's probably until you get to the final project, that's probably the longest training times we'll have is what we did this last week here. And again, if you still didn't get them done, still work on them and see how they go. So we're going to leave images behind and talk about sequential data today. What is often called time series data for things. And we'll look at trying to process time series data in different ways. We'll start with just numbers, a sequence of numbers. So for example, it's kind of handy to just be able to take like a graph like this of stock prices and predict what the stock price will be tomorrow. Or you could look at it as weather predictions. You could look at the weather temperatures and predict what the temperature is going to be like tomorrow here. If you could do either of those things accurately, you would make a lot of money here. So that's what we're going to look at, starting with just numbers, and then we'll move into text and just generating text, the next character or the next word, and it'll kind of form the foundation of our large language models. The chat GPTs and stuff are are kind of set up this way. So this is really, we're looking at a sequence of objects and then predicting the next one. And again, that's what large language models do, is they look at a sequence of words or tokens, and then they just predict the next word or token for that. So let's jump into this first one, just talk about processing data with recurrent neural networks. So again, standard practice is just, what is a time series? It's generally data that is collected and has some sort of regular timestamp on it. So it's usually data that's collected at a regular interval, and often has a timestamp on it. Although we'll see, it doesn't have to have a timestamp on it. It just has to have an ordering generally. So wording, like a sentence, could be sometimes looked at this way. But a traditional time series has, like here, is that like this could be the high temperature of every day. So we have every day, so regular, 1 day at a time, 24 hours apart, and then the temperature at that time for this. So this is what we call a time series. Here's another one. This is 3M's stock price for the last 5 days. And it is done hourly here. Oh, no, it's done every 20 minutes here. So again, we will have this. Now, different with time series, you can worry about this, how regularly do you collect the data? So if we look at this over a year, this will be, every data point here will be a different day for this. And there'll be 365 for the whole year there. But again, if we look at a different time frame, like 5 days, we might collect data every 20 minutes. Or if we just do every day, here we might be collecting data every minute of every day and seeing this. So it's kind of important to pay attention to what is, how frequently are we collecting this data for this. We often start with just a single dimension like the temperature, but we quickly move to higher dimensional data. So again, here could be stock prices of Apple, Delta, Elite, and Medtronics here. And the prices on these days, it was just a couple years. Oh, I'm sorry, I'm just really curious now what Apple price is now. Oh, now I have to look. Oh, it's 180. So it's the same price as it was back then. So I think it's split. So maybe it's actually double the price it was back then. But anyway, so these are the prices. And again, we might have multiple columns, attributes, things we're collecting. So again, here's different stocks. We could have temperature. We could have different things like the temperature, the humidity, the wind speed, different characteristics. Or we could have like the temperature at the Duluth Harbor, temperature in the airport at Duluth, the temperature in Hibbing. So we can have different locations, but you can have, multiple dimensional data here that you're collecting every regular time series. So again, common ones, certainly weather measurements, financial markets, any of these currency exchanges, anything like that. Quarterly, like company data. So we often will see like quarterly reports from companies on company sales, expenses, or like if you're a college, how many students are enrolled each semester. If you're a hospital, we look at like every quarter, operations performed, things like that, procedures done. This sort of stuff is all generally timed. Now we get into stuff that's not necessarily timed, like music. So just a sequence of notes and sounds that we can play. And often there is a time frame given for those. So maybe like there's a time signature. And so you'll be told how frequently the notes should be played there. But sometimes you don't know that. You just have a sequence of notes or sounds that are being played here. And there are standard formats for holding this. And we've had students work at generating music and stuff. So there's a MIDI format, and it's commonly used for this type of stuff in machine learning. There's text, just generate a sequence of letters or words. And again, this is where we're getting into large language models here. Other things like motion capture. Saw a nice report, people looking at people doing exercise and extracting the locations of their limbs, their arms and legs and stuff, and capturing this human figure pose of this data over time. Yeah, we've had students and faculty in our PT department work with gaits and track 3D poses of people walking there. And there's a whole 3D capture lab that the PT department has here that captures this motion data with a set of cameras here. So sensor data, any sort of sensor data, traffic noise, stellar intensity, SETI, radio data. So anything like this, where we've got some sensors out there that are recording data and reporting it frequently. So what do we do with this data? So basically we'll look again at two things. Can we categorize it, or can we predict what the next value is? So categorical stuff is to look at the data and put it into some category. So again, with motion capture, I saw a paper where people were doing motion capture, and then they could tell from that if the person was doing one of a dozen different exercise. So they could say you're doing sit-ups or jumping jacks, or you're lifting weights there, or things like that. Music genres, maybe we could look at a sequence of notes or some music and tell, is this classical or is this jazz, or what is this? Either written on paper or performed here. Sometimes we're just looking for abnormal stuff. SETI data is we're scanning stars for strange anomalous data that might be signs of intelligence out there. And so again, they're looking at the range of normal data and just trying to spot abnormal stuff there. If we have a sequence of tweets of characters, can we tell if it's racist or if it's I saw one where they would look at the sequence of tweets coming out, and then they would just identify stocks, and then some basic analysis of it, if it was a positive or negative tweet, and then they would buy the stock based on the tweets that were coming out of that. This stuff is done, but it's probably not as common as the next one. Prediction is where we see a lot of this. If you can predict stock price values, and a lot of people spend a lot of money predicting stock price values there. It used to be people would buy stocks and pick stocks, but now at most of the investment firms out there, we have computers analyzing, this and trying to predict if the stock is going up or down here. Weather forecasting, a lot of these models, last fall, we had someone presenting actually on campus here as part of our data analytics series, talking about weather prediction and how neural network models are now getting to be very common for this sort of weather prediction. And they're collecting thousands of points of data across the world and then predicting stuff based on that. So I used to have this as just kind of a stretch thing that you could actually try to write a poem with AI. And 3 years ago, people were saying, yeah, but you can't actually do that, can you? And we'd read an article about someone trying to write a musical in London using this sort of stuff, and how bad it was turning out. And large language models have really changed this a lot here. So, and then again, generating music. So I just want to highlight a couple things with time series forecasting that can cause problems. One is seasonality or any sort of regular ups and downs to this. So again, in temperatures or weather forecasting or sales, if you look at the sales of shorts versus pants here, or lawnmowers versus snow blowers, those are all seasonal products, and you'll see a regular up and down to these. And I always think a lot of companies get Minnesota wrong because they seem to do the whole United States. I remember last year, we had this whole, so much snow last year, and it was about this time of year, I wanted to buy another snowblower. I could not find a snowblower because everyone had switched to lawnmowers already, because in most of the country in March you switched to lawnmowers. And again, since they were doing it in other places, they were doing it here. So they were not predicting the seasonality in Minnesota very well. Okay, so besides just up and downs, seasonal or anything related to that sort of cycle, that makes it hard. But we can see these trends. So like this is Apple revenue over time, and we can see it goes up and down and up and down, but there's an overall trend of going up. So there's a upward trend and an inside trend going up and down every time. So we see this up and down and an overall trend. So again, when we have this long trend here, that can make it hard. So like here's monthly air passenger forecast. So his number of people flying every month. And again, we see every year it goes up and down, but over time, it's been increasing. So if we don't take that into account, like these blue lines are our predictions, these blue predictions are going to be wrong, because if humans look at this, you can see this is obviously going up. These blue predictions should be higher. So we're capturing part of this, but not the long-term trend for this. The other thing is like discontinuous observations. We did a Kaggle challenge in this class a year or two ago, trying to find exoplanets, planets in suns outside our solar system. And so there's a couple telescopes that were doing measurements out there, but the telescopes go and look at different stars. But again, sometimes it's cloudy, sometimes it's not, and they can't go to every star every night there. So you would get observations from stars like 3 nights in a row, and then not for 2 nights, and then maybe 4 nights and 1 night, and then miss 3 nights. And so there was discontinuous observations, and that makes forecasting hard too. Okay, so what I want you to do is think of a time series, some data that you deal with. And I'm just going to ask some of you to come up. So think of an example. Describe this data. How is it used? Does it have seasonal fluctuations or other regular changes? Does it change over time? And what do we usually do? Do we try to predict it, generate things from it, categorize it? What do we do? So think of some sort of time series data that you're familiar with. And if I give you time to think, I then have the right to call on you for an example there. I won't call on all of you, but I'll call on AJ because she was late. So right? So. All right, so let's give me some examples of some time series data, some data that's collected over time here. So, Jeffrey, you have something you can give us? Yeah, yeah. I was just in the hospital seeing someone the other day, and yeah, heart rate monitor. They have equipment just to do that, collects it regularly. That's a great example. So, all right, who else? On your phone? Screen time. So yeah, so is your phone tracking that? Yep. Screen time on your phone, you can graph that. You can see how much time you spend. So sleep. Yep. Yep. So if you have what do you have something that tracks you have an app. Okay, I have a Fitbit and that tracks it the same way. It also tracks heart rate and stuff like that. So I can, or steps, I can look at any of that stuff over time there. So those are all good examples. So
like video game server traffic, so like people are logged in.
right. So yeah, if you're playing video game and there's a centralized server, you can see that. You can also see any sort of traffic things like, I don't know if you look on like Google Maps or whatever, right, and you look up a restaurant or something, right? Let's look at Sarah's table. And they'll show traffic at Sarah's table at any restaurant over time, or different hours of the day that they'll estimate. So, all right, AJ.
I was thinking like movie trends, like for like what's more popular, like what type of movies are more popular.
Yeah, okay. So what, like action or
Like
something?
action,
Yeah,
fantasy.
right. They also track, you could just look at, each movie and how much it's making the box office every week too, because so not, you could either look long-term at, or we wanted comedies or action or superhero movies, which ones, or you can each movie. And same, track that sort of stuff is, and same with songs, you can look at it, or and again, now that we're in social media, how many times is this video played each day, or so all we're collecting that sort of traffic or views stuff on a lot of different types of data out there. So a lot of people then track that. I mean, if you're doing any social media and you're trying to make money off of it, you are tracking that because often the number of views is going to, be related to what you're getting as far as that content payback goes. My daughter recorded a whole bunch of calculus math videos and posted them online. And now lately they've been slowly getting to be more views. So they're like getting up to the 10,000 views up there. So, so she was looking at what point, but she can't monetize it because she just doesn't have enough people following her or something like that. But I don't know why there wouldn't be a lot of popularity for calculus explanation videos. You'd think that would be a really popular niche in YouTube. So, okay, so that's our data. How are we going to process this data here? So certainly we could just take some of the data, a sequence of data, and feed it to a neural network all at once there. But how much of that sequence do we feed to the network? And often it varies. So if we're feeding sentences to the network, some sentences are short and some sentences are long. So how do we handle those sorts of stuff? And then how do we handle, predicting, feeding something? And so what we want to do is set up our network so that we can feed it a set of items. But our traditional neural network, when we give it one input and we give it a new input, it forgets everything. We clear out the network between inputs. We give it one input and we calculate everything, and we zero everything out and give it a new input and see. So it has no memory. A traditional neural, and even a convolutional neural network, and we don't want it. So if we show it a picture of a cat, we don't, and then we show it a picture of a dog. When we're showing it a dog, we don't want to think back, oh, but I just saw a cat. No, that's not important that you just saw a cat. The only thing that's important is you're seeing a dog right now there. So we want it to clear out, so we just wipe its memory and show it the next one. But when we're getting a time series data, we don't want to do that. So we have some ways of handling this. One of these is called recurrent neural networks here. So now one thing we can try to do with traditional networks, even though they don't have memory, is we can do a sliding window. So if we have this time series here, 34, 38, 43, 37 numbers, we can then just send, let's say, 5 numbers at a time to our neural network and have it predict maybe the next number. And then we can move, we call it a sliding window, because you can see kind of this red window slides over time. We can move this red window ahead so it'll see the next time here. So we can have a sliding window of inputs to this. So start with the beginning. And again, maybe we're predicting the next number here, or we're trying to categorize it, and we slide it ahead. So this moving or sliding window is a common way of handling these inputs in a traditional neural network. But with this, we only are looking at 5 things, and we don't see long-term dependencies here. So in order to get long-term dependencies, we're going to do recurrent neural networks. So far, our neural networks have been what we call feed-forward. The input layer is connected to the hidden layer. The one hidden layer is maybe connected to another hidden layer, and the next hidden layer is connected to the output. All the connections go only one direction, from the input to the output. But in your brain, there's lots of mixed up connections. There's not just one layer to another to some highest layer. There's lots of feedback connections from one area of the brain to another area of the brain for that. And so we could do the same thing. We could take your output layer and connect that back to like the hidden layer or one of the hidden layers. So the hidden layer would see the output from last time and the input from the new time. So this is what we're often working with, is these recurrent neural networks. These have been around for a long time. I did my PhD on recurrent neural networks, and Jeffrey Hinton was a big person back there and was developing these recurrent neural networks at the time here. We thought these were going to solve and do everything we want. They didn't do very well yet, okay? But that's okay. You can spend your entire, 5 years doing a PhD on something that really didn't matter in the end, but that's okay. Okay, so we did traditional recurrent neural networks, and then we thought, oh, those aren't working very good, so we made some more complicated neural networks, long short-term memory and gated recurrent networks here. So now I used to go over these like 3 years ago. We used to go over these more because we thought these were going to be important. These aren't so important anymore. So we're just going to kind of go over them, but we're really not using these anymore. Okay. So long short-term memory networks, again, we want to try to do more complicated networks. We have an input coming in the bottom here, and then we split it up to different things, and we have it also getting an input from its state from the last time. So it remembers what its state was during the last update, and we get some new inputs. If the new input is really exciting, it sends a signal to forget to just basically cancel out the inputs. So if we see some new exciting input, we forget about what we did before. Otherwise, we can just mix what we did before with our current state and kind of evolve to a new state and send that new state out to the next thing area. And then we're using some sigmoid functions, some tanh functions, some math computations in here on this. And gated recurrent networks had a similar structure for this. And here we can look at kind of these sorts of guides to this. So again, these networks are kind of set up to handle these problems where we are trying to get the data in different ways. I'm not even going to play that video this year. Where we feed some input in to this sequence, and it updates itself. And then what happens is that on these networks, this output here actually wraps back and is the input in the next time frame. But often we draw these kind of as a sequence of values here. These are pretty easy to set up in Keras here. We can just set up our problem, and we can define our neural network here. Where's our neural network here? So here's our neural network here is we just create a sequential layer, a sequential network, add a long short-term network here, add a dense layer. So we can just add these layers, and they'll automatically have, if they're a recurrent neural network, like a long short-term memory, they'll automatically have a recurrent connection built into them for us to use for this. And we're going to use these on Thursday. We'll go over the learning model for these, and we'll try to predict numeric things. So on Thursday, we'll do this recurrent neural network activity and look more at that. So I'm not going to go over them that much today. We'll cover them on Thursday. Now, and those were just predicting numbers and working with numbers. Neural networks work like numbers. So how do we do text? So the next thing we're going to jump into this learning resource on generating text with these recurrent neural networks. And we're going to go through, I'm going to do this. We used to do this as a full activity. I'm just going to walk through it today with you. This is it used to be the Unit 9 activity. Again, we moved it up to Unit 7 here. So again, I'm going to this generating text. I'm scrolling down to this practice activity, and I'm opening that up here. And we're just going to walk through this code and this model to see how it works. So again, we're going to import some values here, or I mean, our libraries here. And again, we've added some new layers here. So besides like our dense layer, we had our convolutional 2D layers and stuff. We've added a long short-term memory layer and a gated recurrent unit, and also just a simple RNN. So these are our 3 new layer types we've added here. So we imported them here. I'm just going to skip this. It used to be you had, if you're running on a GPU here, you had to do something special to get this to work. I'm going to skip that. And then we're going to read in our data. We're going to use text that's out there. So there's some example text here: The Wizard of Oz, the Bible, Alice in Wonderland, and Shakespeare here. So we'll bring in one of these texts. I'm going to do Alice in Wonderland. So if you look at this, the URL, so I have 4 different URLs here, and the URL I'm using here is the Alice in Wonderland URL. If you want to try like the Bible, just switch this to URL equals, and then one of the other URLs like Bible URL. Or if you want to do the Wizard of Oz, Wizard URL. I'm going to stick with Alice in Wonderland. I have a whole Harry Potter sequence also available, but that's still kind of copyrighted, so I didn't want to put it in this notebook. But it's kind of fun to just feed that into one of these things to see what it writes as far as that goes. Okay, so we've got this set up with our text, and it shows some samples text. Chapter 1, Down the Rabbit Hole, is the name of the chapter. You know, Alice was beginning to get very tired of sitting by her sister on the bank and having nothing to do, and onward and onward. So that we've loaded that in. Now we're going to do this character by character first. Character by character is not going to work very well, but we're going to try it. So we're going to get, we need this as numbers. There are 26 characters. We're just going to add each character a number there. Now there's a bunch of other characters in this. So here's a dash, here's a space, there's uppercase and lowercase, here's a period. So we are going to just use what is called a tokenizer here. And the tokenizer will assign numbers to every character in our stuff. We'll scan how many different characters we have and assign them. So like here's Gibbons is a 16, a 6, a 23, a 23, a 5. And again, so GIBB, those two are both 23s here. So 16 is the capital G, 6 is the I, the 2 B's are 23, 23. So again, we're assigning a number to every letter here. You're thinking there are how many letters we want there in our text. There is 42 distinct characters of this. So, and there are 142 characters total in Alice in Wonderland. So we will convert all of our text into characters. All of our characters into numbers, tokens. Now we're going to break our sequence into smaller sections. Remember how we kind of did this moving window? So we're going to show our model 100 characters in a row and then have it predict the next character. So we're going to, this number of steps, we're going to show it 100 characters and have it predict the next character. Do you know how many characters you can show ChatGPT, how many words, and have it predict the next word? Hint, it's more than 100 there. So, but we're just going to start simple. 100 characters, predict the next character here. So now we're going to set up our RNN here. Oops. I forgot I have this code for the scope, and I didn't run this program, this scope thing. I'm going to run this TPU thing ahead because it defines this variable that I actually need down here. So I'm going to run that. If you get this error, strategy scope error, go back up and make sure you ran this one thing that I skipped with the TPU definition. I didn't think we need it, and we really don't, but it generates error if we don't write that. Okay, so here's what we're doing. We're defining our model, and it's going to have a long short-term memory layer with 64 nodes. And it's gonna have another long short-term memory with 64 nodes. And within that, I can specify things like the dropout rate. I can specify recurrent dropout rate with recurrent connections there. And I can also say, are we generating an entire sequence? So if we give it 100 characters, is it just predicting the next one, or is it generating 100 plus the next one values here? So we set this up, this network up. We're compiling it. Here's our summary. There's not many connections here, 63,000 connections. And then we're fitting it to the data here for this. So it'll take a little while to fit it to the data, but it'll fit it to the data for this. Now, in order for this to work, to test it out, we're going to generate characters, but we got to do some stuff because it's going to generate numbers, and we have to take the numbers and convert them back to letters. So we've got to set up some stuff here so that it will predict things. Let's see. So it should be predicting, I'm feeding it in initial sequence here of how R, Y, O, and I think it would predict U, but this is not predicting, it's just always predicting the space here. So it's not doing very well here. Now I can try, if I can predict one character, the next character, I can feed that in as input. So like it's looking at 100 characters and predicting the next character. I can just take that next character I predicted, add that into the input and have it predict the next character and add that in. So this code here is set up to predict the next character and then the next character after that and the next character after that here. So it's looking at how R, U, Y, O, and it's predicting the next character as E. I don't know why E. Again, these systems did not work very well. We tried. We spent years trying to get these systems to work. And sometimes we could tweak them to work better there. But this is predicting this sequence of characters. They're not even words, it looks like. So we can try this again, run this through, and again, still not predicting sequence. Now, if I did some more training, maybe if I went back here to where I was doing my fit here, maybe did it for a longer training time here. Maybe I'd get some better results of this. But this whole character predictions, sometimes it's not often we'll get it to predict actually words or something that looks kind of like words here. So here I'm still training. Again, I'm only training it for, like I say, like a minute here. Often I need to train this for like half an hour on this words, and then it'll get better here. So I'm not training it for very long for this. I'm going to let it train and see if it does better. So again, some suggestions you can do here. Drew networks tend to work better than long-term networks here. So we could add some of those here to our network. So we could go up to our network and try some different values here. So in my network, I was using these long short-term memory networks. I could change them out for like a rule, gated recurrent network here instead of this one. Oops, that's not my comment. Here's my comment. I could maybe not do the dropouts. I could just skip the dropouts if I wanted, and see if that would help, here. Skip these dropouts. I could make this a GRU network too, so I could try out some different things. Maybe train this for a little while longer. I'm not going to train it long because I want it, I'm just demonstrating, but you can try to train it longer, here. And then we can kind of see, this is looking a little bit more like TEAOT. You know, it's looking a little better. That was the previous one. Now I've switched to these new units. We'll train those and see how that turns out. And again, I really should be training this for like a half an hour to get any good results here. So here's the newest one. Now it's generating words. He, the, was, the, he, she, the, was, and the. So it's generating words. It's looking at the character and generating a character that makes a word. We're not getting sentences yet, here. But maybe with some more training, I'd be able to get some sentences out of this, stuff. But one of the problems with this character-based stuff is that characters are almost just too fine of a value to feed into these networks, a lot of times. So in section 3, we're going to look at word-based networks, here. So here we've got our different text, here. We've got the Alice in Wonderland or the Bible, The Wizard of Oz. I'm using Alice in Wonderland again, here. And now I'm going to tokenize these words. And we're going to tokenize them in a bad way first. It's not going to work. And that'll help us understand why we switched to a new way of tokenizing. So here's what we're going to do. We're going to assign every word a number, here. So we're just going to go through, figure out how many words and assign every word a number, here. So we'll start with the most common words. The will be assigned 1 and will be assigned 3. Things like, we treat some of these things as words, even though like a single quote is assigned to 2. The word to is assigned to 4. A is assigned 5. She is assigned 6. Alice, because this is Alice in Wonderland, it's pretty common, is assigned 10. So every word is assigned a number for this. So we can have a whole sequence of our word, our sentence become, or our whole text becomes a whole sequence of numbers here, that we have. And so there are 2,854 different words here. And we're going to do one hot encoding of those words. So we're going to have, now that's a lot. We're going to maybe limit this to 2,000 words here. And we're going to do one hot encoding of 2,000 words. So our inputs will be a set of 2,000 zeros and ones. It'll be mainly zeros, and there'll be only 1 1. So if we want to encode, let's go back up to our numbers here. Oops. Like and is 3. So if we want to encode and, it would be 0 0 and then a 1, because it's the third one, and then 0, 0, 0, 0, 0, 0, 0. If we wanted to do Alice, Alice is a 10. We'd have to do 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. So because Alice is the 10th one over there. So again, we do this one hot encoding here. So again, 1 is encoded like this, 2 is encoded like this. And so every word is 2,000 of these zeros or ones, mostly zeros. This isn't a very efficient way of encoding these values. And it's not going to work very well. But we tried for years trying to get this to work. So we encoded all our values. We then are going to show it a set of words. This time we're going to only going to show it 10 words. It's going to look at the last 10 words and predict the next word. You think maybe you see 10 words, you can predict what the next is. Okay, so now we're going to run our network here. So we have some long short-term memory modules. We have some dropout modules. Here we're doing these separate as dropouts here. And we finish off with some a dense layer here. And then we're predicting the words. And again, we've got to predict there's 2,000 different words. So our output is 2,000 different words here. So we actually end up with a pretty big network. This is a network of almost 3 million parameters here. And then we're going to run and try to get this to fit here. Now, do you remember when we were doing CNNs and if you ran with a GPU or with not, remember like last time I couldn't run with the GPU, I'd used up all my GPU time and it was really slow. And I don't know if you were trying this out. I know some people ran out of GPU time or it wasn't set to GPU for a while and it was working very slow. So with convolutional neural networks and that sort of stuff, GPUs can do a lot of it at the same time. We can process the whole image simultaneously here. Now, with these recurrent networks, we can't do that very well because in order to compute something, you need to get the output and feed it back in. So you have to compute everything on one layer kind of, so that you can feed it back. So it doesn't optimize very well. So these recurrent networks slow things down, really just prevent us from what we call parallelizing, running a bunch of steps in parallel at the same time. And so it's going to be a little slower here. Even if we're running on a GPU, it's still going to be slower here. I'm just going to let this run and I'm going to skip down here. And so this is how we would generate text. Again, we have to take a word, tokenize it, or take a whole sequence of words, tokenize them, feed it in there, and have it predict the next word there. And we have to detokenize that word so we can print it out. But then we take that word, add it, feed it the input with that new word and have it predict the next one. So this code predicts the next word, adds that predicted word onto our input sequence, feeds the sequence back in to generate a new word, adds that word onto our input sequence and keeps looping over. So our code is getting very complicated here. We're not going to go over it, but that's kind of what a high level does. And so we should be able to generate a whole sequence of letters here. She felt forgotten, the subject of outside, as they was begun about their things, that the cook all be remarkable enough. So we're generating words, and we're putting some of them together okay. Forgotten the subject. That could be a phrase about their things here. do rather, very nervous, nervous. So some of this is okay, but again, not really getting up to sentence kind of structures here that we're generating for this. And we got better at this about 4 years ago, 5 years ago. They were able to train this stuff on big sets of of characters. And again, I remember 5 years ago, the BBC tried to write scripts. What they would do for musicals is it was so bad, they had it write 1,000 different plots, plot summaries. And then they went through them manually with a human and threw out 99 of them and found the one that was pretty good and said, oh, computer did this. And they did. And then they had that plot summary and had it write a dialogue for a scene. And again, threw out a bunch of really bad examples that it generated and picked out the one that was working. So this is where we were at a couple years ago. We're training this here. And again, we're training this. This is taking like 2 minutes per epoch, and I'm doing 20 epochs. So that's, less than an hour of training. So that's not that much training time here, but again, more than I can sit in class and wait for here. So a lot of this problem with these words was this encoding, and we're trying to get that. And so in your brain, when you think of certain words, words are kind of related to each other, right? In different ways. So if you think of like boat and fish in my mind are kind of related together. Often when I'm thinking about a boat, I'm thinking about fishing. Or if I think of kayak and canoe and boat, of those three words, how would you see them related in your brain? Which ones are closer to each other? Is kayak closer to canoe or closer to boat there? And we at some point did a whole diagram of the English language and tried to diagram everything and said, oh, boats are here and there are lots of different types of boats. There are sailboats and there are canoes and there are kayaks. And we listed out, people spent their entire lives there, listing out, building this whole listing of the grammar of the English language and trying to say that would help us to this here. It didn't. So I'm just going to leave this there and go back here. So just a preview here is that we've been doing recurrent networks. And one thing we found is that attention was missing from them. And so they added these attention models to this. See if I can get a good view of that. So again, these are our recurrent networks. We're feeding input, and then there's a recurrent connection that's sending the output back to the inputs here. And we look at this in different ways. So there's different ways of looking at this. But we found that attention was important. So if we're looking at a sentence, a sequence of words, and we're trying to predict what the next word in the sentence is. Some of the past words are much more important than others. So if you have a sentence that has a pronoun in it, the noun is important earlier on there. So you need to keep that in mind. And again, if you're talking about, you say, we went to a restaurant and we sat down too, and you want to decide, are you going to eat, or are you going to play a game, or are you going to watch TV? the fact that you're in a restaurant, that is important to that sentence and what you're going to do in that restaurant. So we decided to build in an attention model that when we were training these models, they would look at words and then see how often one word occurred after other words. And if a word frequently was tied to other words, we'd increase that attention module there. So we built these attention modules into these methods. And we thought this long-term, short-term memory would work. It did not work very well. So we eventually created some sort of attention module for this. I'm trying to see. Yeah, so where we would encode the inputs and our predictions, and our attention model would look at, for our prediction, how often was it associated with the inputs here? And we had this special way of doing attention weights there. And so when we looked at, like, for example, if we were going to translate a word, a sentence here, we're going to translate a sentence into French here. If this is each of the words in English here, and we're going to translate that to French, some words, certainly some words are very important in translating. So like August translates basically August in French. Sorry, I don't know French, but some things are switched around. Word ordering changes. So in some sequence of characters, we have to attend to multiple sequences, multiple words to get it correct. And so these sorts of modules were able to look at that. And once we got attention, we realized someone at Google, a team at Google said, do we need to have the recurrent networks? Because recurrent networks are just slowing us down. Are you still training a network? It's just slow there. And if we get rid of the recurrent networks, we can train this so much faster. And so there's an important article called Attention is All We Need. Do that. So we will talk about this attention more later on. Attention is the heart of transformers and all of today's models. So we'll spend more time on attention. So I just wanted to do a preview of that. And attention is going to replace all of our recurrent connections there. Okay, I'm going to do one more thing then. We're still back at tokenizing words. And how do we tokenize words better? So I don't know if we talked about the company Hugging Face. Have you ever heard of the company Hugging Face before? So they are a huge company in machine learning. They're based in France, and they deal a lot with open source models. So going forward, we'll be using Hugging Face tutorials and Hugging Face models a lot for things. So I just want to mention, because I think this is the first time we're even just talking about them. But they have a nice tutorial here, which will walk through how to set things up. So they'll walk through these tokenizers and how we tokenize things. And they do the same thing that we did today. So you can do character-based tokenizers. That's what we tried. And they have a nice video on character-based tokenizers. We get small representations, 26 or 40 letters or something like that. But it's hard to learn context and meanings because cat and car are very similar as far as the letters go, but very different as far as the meaning goes. So often the the similarities between the letters and the similarity don't match the similarities between the meanings there. So the next thing is word-based tokens. But we often end up with 50,000 different inputs and a huge encoding matrix. So this causes us some problems. And what today we use is what is often called subword tokenization or some combination. There are different ways of doing this tokenization and converting words into tokens. Now, once we have those words in the numbers or parts of words in the number, so why would we do parts of words? So like a lot of our words are made by putting words together. So you say common and uncommon. So uncommon, we take the prefix un and put that as a separate token there. And again, often same with suffixes, if you can look at token and tokenization, the ization is just a suffix added to things. So, if you just look at some of these words, decomposed is decompose and an ed added on. And so we would break the ed off. Same with meaning. We would probably we might break that into mean, and then and an ing, and then full. So we might break that into 3 subtokens. Certainly sub word would be broken up into sub and then words sometimes. Okay, then we talked about one-hot encoding. So if apple is 1, chicken is 2, and broccoli is 3, we'd encode them this way. But that doesn't work very well. So we decide to train a neural network to encode our words. So we train a neural network to look at a sentence and see how commonly words got together and then encode these things. So we would send in words, and we would send in one-hot encodings into this neural network and have it create an encoding for this. So rather than having a one-hot encoding of the word with like 2,000 or 10,000 different inputs, we would condense it to maybe 60 different parameters that we'd code this word on here. And so we get these word encodings set up here. And so word encodings are very important these days. So like BERT is one of the first ones that Google created and published. And we can kind of look at how these are set up here. So I'm going to go down to this word embedding projector. This is this last thing, this word embedding projector here. I'm going to do that first. And so we're gonna try to view these multi-dimensional, like 60-dimensional data on words on the screen. So we're going to try to do it in 3 dimensions here. And each one of these dots is a different word here. So you can search for a word over here. So I could search for happy for this. And maybe I should spell happy, right? And it'll show me happy on the screen here. And it'll also show me what other words are close to happy here in this vector space, in this space here. So what, in your mind, what do you associate with happy here? It's interesting. They associate quiet with happy. And right now, since I've been talking a lot, you're probably thinking, yes, you would be happy if it was just quiet in here, right? Happy, quiet. That would be your happy spot right now. Funny, you love, remember, sing. Lucky, baby, beautiful. So these are the words that are associated most closely with happy. Now we actually get into different ways of measuring the distance between things, especially with multidimensional spaces. So you can actually try some different measurements. So sometimes we can try different distance measurements and it will reorder things a little bit differently. So you can actually go with these two different distance measurements here. And you can see, so we can search for another. So just try a different, and again, you can kind of see how everything maps here. Try to see a different word for this. So let's try winter. Here. So here I've got rid of all the other noise and just did winter. And so what do you associate with winter? You're talking about a season, so you're next going to mention summer or spring or autumn. Once you get through those, cold, snow, Olympics. I wouldn't have thought Olympics. Again, this sometimes gets back to, have you seen, when I don't know if you played or watched any of the games where like password where you try to say one word and make them to say another word, or there's a sequence of words and you want them to say that. So you might say winter and you want them to say Olympics? Could be. Months, Finland? No, Duluth is in the list. I just would like to mention that Duluth was not in the list for this. But I don't know what map they have. Maybe this isn't. So again, we encode these words in this multidimensional space, and we can kind of view this and see, and it'll try to encode the words that are similar together. And again, this is actually using, I don't know if you remember PCA and that principal component analysis, we talked about that is reducing this so we can visualize it. There are some other ways of visualizing this. You can set up and view these other ways of viewing this, but I'm not going to go over those too much. We'll just talk about this. So again, you can look at different words and see how they're mapped, how they connect up in this. This Google Explorer also will let you look at things. Remember, what we're going to do is try with these attention to predict what word is next often. So like this, to be or not to be, comma, that is what is the right answer here? And so it's 56% sure that question should be the next thing. Difference, challenge, point, like what is the point? Yeah. So it's trying to fill in these words, and you can actually type in your own words here. I guess no, all we can do is click on different words and how. I thought we could switch. Oh yeah, down here is where we can type in the question as we want. So we could say on this March day, the temperature will be so we can try typing in different sentences here. So I like these little, they have some examples here, like in Texas, they like to buy blank, or in New York, they like to buy blank. So what do they like to buy in these locations here? And again, you can change these words here. And it'll show you these views of what is more likely to be bought in Texas versus New York. And anything near the middle of the line will be about the same. But land, and beer are more likely to be bought in Texas. We should try Minnesota and just see what in Minnesota. What we're likely to buy in Minnesota versus New York here. Fish, land, marijuana is now on the list. So groceries, horses, arts and tickets, perfume. Yeah, that's more New York stuff. So you can try this. And you can kind of see the encodings, how this works as far as the encodings go. You can also get an idea of how bias can play a part in these areas for this. Like, oh, they're talking like Lauren was born in the year of, and then it's kind of predicting what year it was, and Elise was born in this year. So Jane worked as a blank, and Jim worked as a blank here. And so now we're seeing some of the bias in this data here. So barber, Jim is much more likely to work as a barber. Jane is much more likely to work as a model here. So you can, it's things on the middle of this line, they're both about the same. But as you get off of this line down in the bottom left, bottom right or upper left, these are more one way or the other here. And you can kind of see these differences. And again, this is just from, I don't know what data this was trained on. They probably, I forget which data this is. But again, this is just pulling this from the data that they were trained on. And you can see whatever the data they trained on was bias, you know, again, maybe reflected societal biases that we have as far as career choices go. That reminds, okay, I'm going to jump tracks a little bit. Right? So this week for the discussions, you have two options. Option one is you can do a job posting. And some of you may have already done this because this was earlier. We had this in Unit 5. So you may have already done job posting. So you're good to go if that's what you did. Okay, so go find a job using machine learning or data analysts or any things like that here. What do you need to know to do this job here? The other thing I'm going to start, and I think I'm going to have this every week, is something from AI news there. So if you see something in the news you just want to share every week, post that. So I want, and again, it can be an article if you read. Reading is these printed versions of like YouTube. It's just they don't have any video, it's just printed words. So if you ever see that, you can look at that stuff. Or again, you can do a video or a podcast or social media posts. I don't know how to get a URL to a social media post, but that's your job, not my job. So you should be able to figure out that, I hope. So, and I want a headline from it or some sort of title. I want a link to the resource. And then I want your summary of why it was important. So, and then if you reply, I want your reaction and a follow-up article or resource of some sort on the same topic. Because like, have you guys, I don't know what your news feeds is, but have you guys been watching Gemini, image, bias? So if you haven't been watching any of the news on the newest releases of Gemini here, you should be watching that. Just for example, here, let me just grab this. in a couple, maybe even next week, pretty soon we'll start talking about image generation stuff. These tools for generating images, and we'll train some of those. But this was a couple years ago, and I forget what we're using here, what model we're using. Stable diffusion. We're using an old version of Stable Diffusion. And again, reflecting cytobiots, I ask for a college student ice fishing in Minnesota. I just get generally white males ice fishing in Minnesota here. Or if I ask for university students fishing in Minnesota here, I tend to get white males fishing in Minnesota. Tends to look a lot like my old my friends always thought it was funny that I have very few pictures of my childhood where I'm not holding a dead animal. Almost every picture I have from like age 4 through 14, I am holding a dead animal in some ways. So, okay, but Gemini, they wanted to counteract this bias here, like gender bias and stuff like that. So they specifically trained it after the fact to eliminate bias from their image generator. And it did not go very well. So someone can post articles to that. It's really interesting. So again, you can do a news article this week for that also. All right. Questions on this? Thursday, we'll do our learning activity on generating sunspot data or something really fun like that. I always think if you can generate sunspot data, you can then predict the stock market. If you can predict the stock market, you can be rich. So, okay, we'll see you on Thursday.